So in the previous video, we have learned about the universal language and the universal Turing machine. At that point, I mentioned that one of the big questions that we want to answer is LU a recursive language? Is it a recursively enumerable language? Or is it a non-recursively enumerable language? So that's what we want to determine. It's very simple to observe that it's actually a recursively enumerable language for sure, right? Why is it so? Because look at this. LU is the language accepted by the universal Turing machine, right? And remember that a universal Turing machine is also a Turing machine, which means there exists. So what does this imply? This implies that there exists a Turing machine, which is nothing but your universal Turing machine. There exists a Turing machine, which is nothing but your Turing machine that accepts LU. If there exists a Turing machine, it is by default recursively enumerable. So there is no question of non-recursively enumerable because there exists a Turing machine. Now the question is between recursive and recursively enumerable, because some recursively enumerable languages are recursive. Look at this, we know that, right? So if these are all your recursively enumerable languages, some of them are recursive, right? So now our question here is LU a recursive language or a recursively enumerable language? So what is the concept behind them? If I have to prove that LU is a recursive language, that means I have to prove that there exists a Turing machine that always halts. So let me write it down. So there exists a Turing machine that halts and that accepts LU. That's what I have to prove, right? So again, there is a special term for Turing machines that halt. Turing machines that halt are often referred to as total Turing machines, right? So a total Turing machine is a Turing machine which always halts. There is also a term called decider halt. They're also called as deciders because they can definitively decide if a word belongs to a language or not, because they are always halt, right? So whenever I use the term TTM, it means it's a Turing machine that halts, right? It's called as a total Turing machine. Now what we have to prove here is there exists a total Turing machine or a Turing machine that halts that also accepts LU. That's what we have to prove. Now I can argue intuitively. So let me give you an intuitive argument on why LU is not recursive. I'll give you an intuitive argument, then I'll also give you a formal argument. Okay? Because getting the intuition is sometimes important. What is LU? Think about it. What does LU consist of? LU consists of your code for machine M. I'll just write, instead of writing code for M, I'll just write M, right? So M here basically means the machine's code in binary and word. These are the words that the universal Turing machine takes, right? So LU is, remember, LU is the language accepted by the universal Turing machine, right? That's what it is. Now, if I give this input, this Turing machine itself, look at what do I have to determine? What do I have to determine? I have to determine if W belongs to M. Or in other words, to determine if LU, look at this, for LU itself, the Turing machine that we have is universal Turing machine, right? Now look at this. I can determine if this belongs to LU or not. This is, suppose given some string like this, where I have a code for M and I have a W. I have to determine. So my question here is this. My question here is, does this Turing machine accept W? Which means, does this belong to LU? That's my question. Now to determine this, what am I doing here? I'm simulating. So to answer this question, I am simply simulating my W and M on my universal Turing machine. That's what I'm doing, literally. Now imagine if M is a Turing machine that never halts, because this can be any Turing machine, right? Now, nobody stops me. Imagine this M itself is a Turing machine that never halts. Okay, look at this. Imagine if this M itself, so if M is a Turing machine that doesn't halt. So let's assume for simplicity that doesn't halt on any input. Let's say, just for simplicity, on any input. So whatever you give. So, or let's assume it doesn't stop on, to make it simple, that doesn't stop on W. That doesn't halt on W. Now, when you're simulating it, what happens now? You're trying to simulate W and M. You're trying to simulate W being ingested by M. But if this, remember, this Turing machine can be any Turing machine. And we know that there are Turing machines, right, which never halt. Because we can write programs. Again, remember, a Turing machine is equal to a computer program, right? So I can always come up with programs which always get stuck in infinite loop, right? I can always do that. Right? So now, if M is a Turing machine that does not halt on W, what happens then? Then my universal Turing machine, which is simulating W being ingested on M, can never decide whether W is accepted by M or not. It cannot accept it. It will also get stuck. See, my simulation also gets stuck in an infinite loop. If this is the case, my simulation also gets stuck in the infinite loop. If it gets stuck in the infinite loop, this decision can never be taken. Look at the intuitive logic here, which means this decision can never be taken. If I cannot always decide, look at this, I'm not able to decide. I'm not able to conclusively decide this way or that way. Which means this Turing machine, if it gets stuck in an infinite loop, there doesn't exist a total Turing machine, because a total Turing machine should always halt. Right? This is one intuitive way of arguing about the LU, the language LU being recursive. But again, this is just the intuitive. This is more of a commonsensical, intuitive perception of it. Because how do we, again, this all boils down to our simulation of ingesting W by Turing machine M on UTM. Right? If M itself is a Turing machine that doesn't halt on W, this simulation will get stuck in an infinite loop. If this simulation gets stuck in an infinite loop, I can never answer this. Which means I don't have a Turing machine that halts. Which means LU is not recursive. Okay, that's one way of arguing about it. But this is only an intuitive, logical argument. There is a much more formal argument which we will show about. Again, while this intuition is a good baseline, the formal argument is very, very important. Okay, so let's go and formally prove this, that there doesn't exist a total Turing machine or a Turing machine that halts, that accepts LU. Let's do that very, very formally. For that, there is a strategy called as reductions. Again, please remember that this is one of the most innovative ideas and one of the most useful ideas in the whole of computer science. Right? So a reduction is a strategy of proving or disproving something. Okay. Again, this idea itself is something that is useful not just in theory of computation. This is also useful in algorithms. Little later in this chapter, we will learn of concepts called as P, NP, etc., where we will reuse the same concept of reductions. So reductions is an extremely important proof strategy. Again, this is something that while I learned it in theory of computation, this is something that I've used extensively in my own career, especially when I'm designing algorithms, especially complex algorithms, right? So let's try to prove that LU is recursively enumerable, but not recursive. Again, we have given some intuition here, but let's prove it formally using the concept of reductions. Okay, let me show you how reductions work. Let me prove the whole thing, then I'll come back to the logic behind reductions themselves. Okay, so first let's assume. Reductions always start like this, right? So let's assume that LU is recursively enumerable. Right? Let's first assume that LU is, so I'll use 2 lines here because this proof takes a few steps, right? So let's assume LU is recursive. Okay. What does this imply? This implies that we can decide. See, remember, we can always decide if LU is recursive, which means there exists a total Turing machine. A total Turing machine always decides or halts, which means we can decide if W belongs to LU or not. Right? If LU is recursive, which means we have a total Turing machine that accepts it. Right? If there is a total Turing machine which always halts, I can always decide. if this is true using a total Turing machine. So let me call that using a total Turing machine or a Turing machine that always halts. So instead of saying Turing machine that always halts, I'll just say total Turing machine or a decider. Okay. So let's call this total Turing machine as MU. Again, I'm calling it MU because this can help me decide if W belongs to LU or not. Or I can also think of it, if you want to think about it from algorithms viewpoint, or we can decide if W belongs to LU using a total Turing machine or an algorithm. So what is an algorithm? If you recall what we learned in algorithms, whenever you write an algorithm in any programming language, an algorithm always halts. It always terminates. If an algorithm goes into an infinite loop, it is not called as an algorithm. One of the most important requirements of an algorithm in computer science is an algorithm always halts. Right? So let's assume, again, I'm trying to give you the context both from Turing machine's world and the algorithm's world here. Right? So let's assume this algorithm, I can write it as AU. Okay. So let's assume LU is recursive, which implies that we can decide, again, I can do a by implication here. Okay. If LU is recursive, then I can decide if L belongs to LU, if a word belongs to LU using a total Turing machine. That's a definition of LU being recursive. That's a definition. Or I can write a computer algorithm. Let's call that algorithm as AU, which always halts. Again, a total Turing machine is equal to an algorithm. Because an algorithm always halts, a total Turing machine also always halts. Right? Very, very important equivalence. This is, again, I just want to give you the algorithm's viewpoint also here a little. Okay. So this is my assumption. So let me write this as my assumption. So let me start this as my assumption. Okay. This is my assumption. Now let's go with the flow. Okay. Now let's take a diagonalization language. So let's take our LD. Okay. You might wonder, why the heck are we taking diagonalization language here? Everything will fit into this proof. Please hang on. Okay. Please stay with me for a few minutes. You'll understand why LD is important in this proof. We are proving about LU, not about diagonalization language. We know that LD is not recursively enumerable. We know this. We've already proved this. We've already proved it using the diagonalization table in one of the previous videos, right? So let's take LD, right? So let's take an instance. So we call this as an instance of the problem. Okay. Let's take an instance of a membership problem. So let's take an instance of membership in LD. So what does that mean? Okay, this might sound very rocket sciencey, very complex term. What it means here is, let's say I have a word W. Okay, I want to determine if W belongs to LD or not. Okay, see, this is basically, what is this? This is a membership question. This is a question about membership in LD. What am I asking? Is W a member of the language LD? But here I'm taking an exact instance. I'm taking one W. I'm not saying I'm just taking exactly one W. I'm taking an instance of this membership problem. Okay, this is called the membership problem. Membership problem basically says, is the word belonging to a language? That's what is the membership in a language problem basically. I'm taking an instance of it, which means I'll pick some W. I can pick any W, by the way, but I'll pick one W and I'll ask this question: does this W belong to LD? This is called an instance of a membership problem. Okay. So I've taken the instance of this membership problem. Now I'll try to solve this problem. Okay. Again, here, only thing I'm assuming is that there exists a total Turing machine. The only assumption I'm making here is there exists this total Turing machine MU that can decide if W belongs to LU. That's it. It has got nothing to do with LD. Now to solve this problem, this is a problem that I have, right? So this is a problem that I have. Now I'll try to solve this problem, assuming that I have a solution for this. Look at this. I'll try to solve this problem, assuming that I have a solution for this. So let me go step by step and show you the arguments that I'll make. Number one, right? First I will check. Okay. So look at this. Now I want to determine this, right? I want to determine this. What is this? What does this mean? What does this mean logically? This means is W. See, W belonging to LD basically means, this basically implies, again, this is equivalent to saying, is W accepted by a Turing machine represented by W itself? So not accepted by, sorry. That's what this belonging. If W belongs to LD, that implies, see, what does W belonging to LD basically means? It means W does not belong to the language which is represented by W itself. What is MW? MW is a Turing machine whose binary code is equal to W. Again, if you've forgotten this, just go back to this. Where are we? So what is LW? LW is the set of binary words which do not belong to the language which do not belong to the language accepted by the machine I. Right? So if you take the same word and if you use this binary word, if you interpret this binary word as a Turing machine, if this word doesn't belong there, then such a WI belongs to LD. That's a definition of diagonalization language, right? So, okay, so this basically means this. So this question, whether W belongs to LD or not, is equivalent to asking, is basically saying, is the word W, does it not belong to the language which is accepted by a Turing machine MW, where MW itself is a Turing machine that is represented using the same word W. Okay, that's how I'm writing this. Now let's take the next step. Now to answer this question, now we have taken a membership question and we have converted into a acceptance by a machine question, right? So look at this. This is a membership question. This membership question we have translated into a Turing machine problem, right? So now let's go step by step. First I will check. Now to answer this question, these are the steps that I'll follow. First I will check if MW, check if MW is not valid. I can easily check this. Look at this. I can write a algorithm, or I can design a Turing machine. Look at this. What am I doing here? In these steps, in these 1, 2, 3 steps that I'll go through, I'll actually design so this whole thing is called the reduction algorithm. Okay, this whole thing is called as the reduction algorithm. You'll understand why it's called the reduction algorithm, or it is called as the reduction Turing machine. Okay, so this is also called as a reduction Turing machine, or reduction total Turing machine, or the reduction algorithm. Okay, so let's go step by step again. Everything will fit in place. This is a slightly tricky concept, but once you see the whole picture, everything will fit in place. Trust me. Okay, so let's assume if MW is not valid, right? What does this imply? This implies that the language accepted by MW is null set. That implies that W is not accepted by is not accepted by MW, right? W is not accepted. So I'm able to answer this question. So W doesn't belong to this, which means what does this imply now? This implies that W belongs to LD. Cool. If MW is not valid, problem solved. I can check if MW is valid or not using a Turing machine. I can easily design a Turing machine, or I can write computer code, an algorithm. I can write algorithm in C, C++, Java, whichever programming language you want. I can write a computer algorithm which always halts, which can decide this. Or I can design a total Turing machine which can do this, number one. So step 2, second part. Okay. So second part. Let's assume if it is valid. Otherwise, if valid. If valid. If MW is valid. Now what do I do? If it's not valid, the problem was simple. If it is valid, what I'll do is this. Remember, I'm assuming that I have this total Turing machine MU, or this algorithm which, given a word, can decide if it belongs to my LU or not, my universal language or not. So what I'll do now is I'll take this word W, I'll concatenate with 3 ones and this. Now if you notice this, what is this? This again, this representation, I can think of this as a Turing machine. I can think of this as Turing machine W, right? Or I can think of it as MW, right? If I take a word, if I take a valid Turing machine word, I can think of this as MW. This is my input, right? This is my input, right? So this is my delimiter. Look at this. I'm taking the same W now. Again, I'm only worried about this question now. I'm taking this W. I'm concatenating 3 ones and then W again. I can do this. I can do this very easily. And by doing this, I can now interpret it as, I can interpret this such that this is nothing but your MW. This is your input. Now I'll ask this question. If MW is valid, first I'll construct this. I'll simply construct this. So I'll simply construct this. Once I construct this, I'll interpret this as a Turing machine, 111, an input. Now when I have this, remember, here I'm saying that I have a total Turing machine which can decide this. Which means now pass this W111W through my machine MU. Look at this, I can pass it through my total Turing machine. Remember, mu always accepts or rejects. Mu does not get stuck in an infinite loop. That's what we assumed. Let's not forget that. We assumed that when I pass W1111, right, this I can pass it to my mu. Mu is a total Turing machine that can decide this. We assume that it's a total Turing machine. We assume that such a total Turing machine exists, right? So if it accepts, what does that mean? So let's look at two parts. If this accepts, what does that mean? It means W belongs to language accepted by MW, right? That's what it means, right? What does this imply? This implies that W does not belong to language accepted by MW, right? So in this case, what do I say? Suppose if this happens, what does this imply now? This implies that W belongs to LD. This implies W belongs to LD. Now this implies W does not belong to LD. Right? Very simple logic. Look at the flow. I assumed that I have a total Turing machine mu which can decide if a word belongs to my universal language or not. Or in other words, my mu, look at this, my mu is a Turing machine, right? I'm assuming it's a total Turing machine. That's the assumption I started with. Because it's a total Turing machine, there are only two outputs. There is no infinite loop here. Look, this is very, very important part of the logic. Very, very important part of the logic. Okay. Now look at this. Now everything breaks down. Now look at this. We know at the very beginning, we know that LD is not recursively enumerable. We have proven this using diagonalization. Using a different method. But now, what am I doing here? If you give me a diagonalization problem, see, this is a diagonalization problem, right? I'm giving you an instance of a diagonalization problem. By using some innovative method, by using some algorithm here, I'm able to convert that into a problem of finding if W belongs to LU or not. If there exists, again, here I'm assuming that this is a total Turing machine. So if there exists a total Turing machine like this, then given any word, I can determine if this word belongs to LD or not. I can determine that, right? Using a total Turing machine. What am I doing here? If you look at a block diagram, look at the block diagram here. This is again called as a reduction diagram. You gave me a word W, right? You gave me a word W. Here I'm assuming that I have a total Turing machine for LU, right? You gave me a W as input. Now I'll design a total Turing machine. I'll design a Turing machine for LD. I can design a total given. So let me write this down here. Given a total Turing machine for LU, I can design a, see, I'm assuming that I'm given this. Okay, that's the assumption we started off with, right? Again, this whole logic can be understood using this single diagram. Very powerful diagrams called reduction diagrams, right? So given, suppose if somebody gave me this, I took your W, I copied the W. Then I constructed W1111W. I'll give this as the input to my TTM, my total Turing machine. This total Turing machine always either accepts or rejects. If it accepts, look at this. If the total Turing machine accepts, that means the word doesn't belong to LD, right? It means the word doesn't belong to LD. So if it accepts, I'll reject. If it rejects, I'll accept. Because of this, look at this. If it accepts, I'm rejecting the fact that so basically I'll reject W because W doesn't belong to LD. If it rejects, I'll accept because W belongs to LD, right? So if there exists, so given there is a Turing machine for LU, I can construct a Turing machine. I can construct a Turing machine which accepts LD. This is the architecture of my new Turing machine for LD. My Turing machine LD takes this input. It can construct this. It can easily construct this by using multiple tapes. And it will simulate the total Turing machine for LU that you have. If this accepts, I'll reject. If this rejects, I'll accept. But I already know, this is very important, but I already know that LD itself is non-REL, which means there is no Turing machine for it. Right? So we know that there does not exist a Turing machine that accepts, LD. We know that we have proven this using diagonalization. But now what we are saying here is, if, see, look at our statement. If, okay, so let me write this like this. Okay. If there exists a Turing machine for LU, then I can construct this. And I know that this construction is not possible. I know this is not possible. because we've already proven it using a different strategy. I know this is not possible, which means this also should not be possible from logic. Look at this. If A implies B, if A then B, but B itself is false. If B is false, I can conclude by proof by contradiction. See, what am I doing here? I'm proving by contradiction. First, I assumed this is true. And I said, if this is true, then I can also construct a Turing machine that accepts LD. Right? But I already know that Turing machine for LD is not possible, which means what I got here is untrue. Right? We know that, so we already know this. But if this exists, if the Turing machine for LU exists, I can construct a Turing machine for LD. But we know Turing machine for LD cannot exist, which means this cannot exist. Look at the whole proof structure here. This is proof by contradiction. Okay, so what strategy did we use here? We used proof by contradiction. We assumed something, right? We assumed that something is true. Again, we took an instance of a membership problem, and by using a simple strategy here, by using a simple steps, what steps did we use? We copied W, we constructed W111, and then again, there is one more step here, which is we first verified if MW is valid or not. Okay, we can also call that as one other step here, which I have not written, right? But if there exists a total Turing machine for LU, I can also construct a Turing machine for LD. But I know that Turing machine for LD does not exist. Hence, by using proof by contradiction, I can conclude that total Turing machine for LU does not exist. Look at this. This is very, very interesting logic. Very, very interesting proof strategy. This whole thing is called as reduction. Proof by reduction. This is one of the most useful and I would say one of the most fundamental ideas for proving anything in theory of computation and advanced concepts and algorithms like P, NP, etc. Now, let's look at the big picture here. Right? So what did we start with? How did our reduction work? In our reduction, again, this is very important because a lot of people make a mistake here. We took an instance of a membership problem in LD, right? Now we said, given this problem, I can translate this problem into an instance of whether W belongs to LU or not. And to translate this instance to this instance, we used a bunch of steps. Look at this, to take this problem from this problem to a problem of determining membership in LU, right? We use these steps, right? Step 1, step 2, step 3, right? We use these steps. These steps are called as reduction Turing machine or reduction algorithm. So these steps, so if I can take an instance of this problem, from this problem, if I can arrive at an instance of the other problem using an algorithm, what is an algorithm or a total Turing machine? This algorithm or total Turing machine is called the reduction algorithm or the reduction total Turing machine. If I can do this, look at this, look at the whole strategy. First I assumed that there exists a total Turing machine for this membership problem. First I assumed that. Then I said, assuming that this is true, if I can take a problem of the membership in LD, assuming that there exists, so I assume that there exists a solution. Okay, this is my assumption. My assumption was that there exists a solution for this, or there exists a Turing machine for this. When I say solution, what I mean is there exists a Turing machine for this. Right? That's what I started off with, or a total Turing machine. Okay, let me write it more precisely to avoid any confusion. There exists a total Turing machine for this. That's what I assumed. Now I said, take this problem, take an instance of this problem. Given any instance of this problem, I can translate it into instance of this problem using a Turing machine. Which means now I can answer this question using this Turing machine followed by this Turing machine. Okay, right? I can combine two Turing machines also. I can combine the logic in this, again, this total Turing machine and there is a total Turing machine. I can combine these two total Turing machines and construct another Turing machine. Right? I just have to simulate this on one tape, simulate this on the other tape. Very simple, right? Which means now, if there exists a Turing machine here, there exists a Turing machine for this also. But we know that that there is no Turing machine that accepts LD, which means everything breaks down. So look at the flow here. One common mistake that people do is, instead of taking an instance of LD and translating that into an instance of LU, people do it the other way, which is incorrect. People take an instance of LU. people take an instance of membership in LU and translate that into an instance of membership in LD. That is not correct. You have to go from this problem to this problem. And the logic here is very simple. Look at the logic. That's why these diagrams are super duper useful. These diagrams are super powerful also. First, I assume that I have a Turing machine for LU or a total Turing machine for LU. If there exists a total Turing machine for LU, I can construct a Turing machine for LD using this bunch of steps, right? But I know that there is no Turing machine for LD, which means this is not possible. Proof by contradiction. That's the whole logic of reductions, right? Very, very important concept here. Now one more interesting aspect here is this. So now we have seen, look at this, look at this diagram here, right? These are my recursive languages, and I know recursive basically means decidable, right? I know recursive basically means decidable because for every recursive language, there is a Turing machine that always halts. If a Turing machine always halts, I can decide whether a word belongs to the Turing machine or not, right? So it always halts. So you can always think of recursive languages as equivalent to decidability, right? Then you have recursively enumerable languages, right? So recursively enumerable languages and non-recursively enumerable languages, both of them are undecidable. Only this is decidable. Everything outside this are undecidable, right? Membership in these languages, membership in rec or recursive languages is decidable. Membership in REL is not decidable. Membership in non-REL is anyway not decidable. Now, if you notice, my LD belongs here. My LD is a non-recursively enumerable language. My LU, we have shown, is a recursively enumerable language, but not